Okay, so looking at a couple of harder examples now, we're asked to show that y equals the root of x plus 1 is always increasing. Now this isn't a show, but we could do this. We could just do it to know that it is always increasing. We could draw a little sketch. Well, a root function is half a sideways parabola. So that plus 1 in there moves it 1 to the left. So that's what my graph looks like. Now if I look at that, I'm always going to have a positive gradient. Okay, over here it's pretty steep, it flattens out over here. Over here it's almost zero. For all intents and purposes it is horizontal, but it never becomes horizontal. So that's not a proof, that's not showing that it is, but that's knowing that it is and that it does tie in with that graph of its function very nicely. But let's go and show that it is. So I've got y equals x, the root of x plus 1. Which I'm actually going to straight away rewrite. I'm going to call that x plus 1 to the power of a half. Now we're going to use the chain rule here. So I write down my power. I write down the derivative of my bracket. I rewrite my bracket and I drop that power by 1. Okay, we're going to neaten it up here. So my negative exponent there means it goes into my denominator. So I've got x plus 1 to the half. Well, straight away that's a root function. Okay, that's what we end up with. Now let's look at this. We're asked to show that it's always increasing. Basically what we need to show is that that is always positive. Well, straight up, let's define our domain for this function here. Well, my domain is that x is greater than or equal to negative 1. Okay, in that function there. When I sketch this guy, that's my domain. Now, if we take that down here, well, straight away, if I put in any value here that's bigger than negative 1, then I'm going to end up with a positive answer. So that means that y dash will be greater than 0 for x greater than negative 1. So therefore, y equals the root of x plus 1 is always increasing. Now what you'll note is that I haven't included an equal to sign there. There's a reason for that. That's because I can't have a value for this first derivative when x is equal to negative 1 because I'll end up dividing by 0. So what we say is we just can't find the value of the first derivative there. We say it's not differentiable at that point. Okay, so it still has a y value. Its y value at that point of negative 1 is 0, but it just doesn't have a value for that derivative. Alright, another harder example here. We're asked to show that y equals x on x minus 5 is decreasing for all x. Now, unlike our previous example, we can't draw a simple little sketch here. So we know this is going to be some sort of hyperbolic function. We also know it's going to have a limit where x cannot equal 5, so that's why we have that restricted domain, but we really can't sketch that. It's an extension 1 problem. But what we can do is find its derivative. So we know that y equals x on x minus 5. Well, if I want to find dy on dx, well, I need to use my quotient rule. Remember our quotient rule we have u over v, where u is our top function, in this case x, and v is our denominator function, which is x minus 5. And then, well, therefore u dash is 1 and v dash is also 1. So actually, as far as the quotient rule goes, this is going to be a pretty nice easy one. We of course cross those over and we do vuv, so it's v u dash, so one lot of x minus 5 minus u x times 1 over the denominator x minus 1, which is our v, sorry, x minus 5, all squared. What do we end up with? We've got x minus 5 minus x over x minus 5 all squared, which is equal to minus 5 over x minus 5 all squared. Okay, well, what are we asked to do? We're asked to show that it's decreasing. Okay, well, how are we going to do that? Well, if we look at this expression here that we've generated, we noted that the denominator, no matter what number I put into the denominator will be positive. Well, now, of course, that's with the exception of our value x equals 5. But of course, we've established that x cannot be equal to 5 because then we'll have a problem with our dividing through by 0 up here and here. But in either case, x can't be 5, we've already established that. But for anything else, our denominator is going to be positive because if I put in 4, if I put in 6, if I put in 0 for x and I square that, well, I'm still going to end up with a positive number. If I put in a very large positive, a very large negative, a very small positive or negative, I'm still going to end up squaring that so I get a positive number. Well, if I end up with and my numerator will always be negative. Okay, so if I have a negative over a positive, my result is negative. So therefore we know that dy on dx is less than 0 for all x. And of course that's x not equal to 5. That's our restricted domain. And then therefore we are decreasing for all x. Okay, now obviously it doesn't mean that our gradient isn't changing. Of course it's changing. If I put 0 in there, I'll end up with a gradient of -1. If I put a very big number in there, I'll end up with a very small gradient. Now we could use that to try to draw some sort of sketch, but as I mentioned, that's well beyond what we need to be able to do. The main thing is you can recognize that no matter what numbers we put in here, I'm sorry, it's actually in here, we end up with negative value for dy and dx, so it's decreasing for all x.